But why it's not working from here? Because I have already shared to the Webex team, but this time it's not working.
तो मैं बता रही थी क्यों नहीं हो रही।
Okay, sir. Yes, sir.
Yes, sir. You're not getting voice, sir.
So here is the various images. Various images. We have to image the features. Then we have to train and then label it, learn the model. On the same, we have testing it and image the feature, learn the model and prediction, and we'll get the prediction. This is the one scenario of the machine learning models. Next one, please. Next one. Next one. So these are the some feature we have taken. Next one. Next one. This is the example of training example how it works. So we have shown you through the functions how it works. Next one, please. Next one. Next one. So what is classifier in the machine learning algorithm? A classifier is a machine learning, is an algorithm which automatically order or categorize data into one or more of a set of classes. One of the most common example is an email classifier. You can see that scans email to filter them by the class label. This one is the spam or not spam or the business and so on. There are many categorization. So they are using this classifier. Okay. Machine learning algorithms are helpful to automate tasks that previously had to be done manually. They can save huge amounts of time and money and make business more efficient. Now, what is the difference between classifier and then model? A classifier is the algorithm itself, which is defined on the rules used by the machine to classify the data. A classification model, on the other hand, is the end result of your classifiers. Okay, what is your result that model will work on? That is the that is the model is known as the result of the classifier is known as the model. Here you can say the model is trained using the classifier, so that model ultimately to filter your data. Next one, please. Next one. Next one. Next, please. Next one. There are various functions, that is linear function, regression function, and so on. These are the example how to categorize the functions data. Next one. This is the signum function we are using here. So there are many classifiers to choose from. That is support vector machine, neural networks, naive Bayes, Bayesian network, logistic regression, randomized forest, and so many algorithms exist. Many classifiers exist. Okay, so you can apply on the applications based. There is a you can't say that this classifier is the best one, because it depends upon the applications. So no one is based. It depends upon the application which one is more suited for that application. Next one, please. Next one. Next one, please. Next one. Okay, these are the some learning objective training and inference, which is useful for these classifiers: naive Bayes, logistic regression, linear regression, kernelized regression, and so on. Next one, please. These are the learning objective training and inferences. Next one, please. So now let us see. After discussing these things, let us see what are the paradigm shifts in healthcare. So first one shift is the pattern from rule-based system to the data-driven intelligence. Before the earlier, what happened? The healthcare AI used deterministic rule-based expert system. If then logic they are using. Okay, limited adaptability was there. Required manual updates are required. But now the shift is that now we are using the machine learning models learned directly from real world data. Okay, EHRs, radiology images, genomics, wearable, and system continuously improve as more data flows in to enable predictive diagnostic rather than the reactive treatment. So that is the paradigm shift. Okay, for the example, if BP is high 2x, then you have to the hypertension risk earlier. Now we have to predict, the model learns thousands of patterns to predict stroke months before symptoms. We can predict if your blood pressure is high, then you can predict you have the probability that you will get the stroke in the within 1 month or 2 months and so on. So that is the paradigm shift in the rule-based system to the data-driven intelligence. Next one, please. Second one is from descriptive analytics to predictive and perspective analytics. In the old system, we are using the descriptive analytics. What happened, reports, dashboards, and so on. But now we are able to predict and prescriptive analysis. What will happen? The machine learning forecast. What happened to the next phase? What should we do? AI assisted treatment plans. Yeah, they will give the treatment. They can suggest you. They can predict your health requirement and so on. So predicting sepsis 6 hours before onset, recommending optimal drug doses using reinforcement learning. That is the next shift. That is, we are going from descriptive analytics to predictive and prescriptive analytics. So these are the this one is the next shift of the healthcare system through machine learning and the AI. Next one, please. Next one is the from fragmented data to the integrated multimodal intelligence. Okay, traditionally what we shared data, lab results, radiology, physician notes, genomics, wearable data, these are available. Now the shift is, now we have integrated all the models. Okay, so AI integrates multimodal data in one model. So here what happened then, the more accurate diagnosis we can get, personalized treatment we can get, and real-time monitoring of the healthcare system can be done through the AI and machine learning algorithm. So this one is the third shift of the healthcare systems. Next one. Now, next one, please. Next one. Okay, now single task models, foundation and generative models are available. Okay, so what is here? A splice model for one task: detect tumor, classify arrhythmia, and so on. Okay, we can detect the different tumors and types of tumor. Now what we can do using the machine learning and AI, large medical foundation model, जैसे MedGPT, BioGPT, RedGraph, LLaMADE can perform better results. We can give the diagnosis, we can give the summarization, we can generate report generation, we can image interpretation. Okay, pathology reports we can done through the in the automated form. Drug design we can done through the machine learning models. Patient communication easily can be done. You can get the report instantly. You can advise from the doctors instantly and so on. So here is the safety generative AI to clinical co-pilots format, drafting discharge summaries, interpreting lab reports, turning the radiology images into the structure test and so on. Okay, so these are the next shift from the traditional model to the AI and machine learning models in the healthcare system. Next one, please. Now population level care we can do to precision level. Okay, machine learning A levels treatment tailored to the genes, metabolism, lifestyle, disease stages, comorbidities. Okay, these things can be done through the machine learning model in the precision format. For the example, cancer immunotherapy personalization we can do it, predicting which antidepressant works for which patient, AI guided insulin dosing for the diabetics and so on. These can be done through the machine learning AI models in the precision format. Next one. Human only decision making to human AI collaboration. We can make the collaboration through the machines as well. So AI is not replacing doctors, but enhancing their capabilities. Okay, so shift in workflow is AI tries cases, doctor review it, AI highlights abnormality, radiologist confirms it. AI predicts risk, doctor plan intervention it. So what you will get in the result? Faster diagnosis, reduced workload of the doctor, lower human error, even reduced workload of the doctor, paramedical staff, and so on. Okay, lower human error, better patient outcomes we can give. Okay, so we can give the better result using the paradigm shift in the using the machine learning and AI algorithm. Next one, please. From static algorithm to continuous learning systems. Okay, or continuous learning system, continual learning you can say. Continual learning is the new mod. In earlier, train once, deploy forever. That was the method. Now we have continuous learning from new patient data, updated guidelines, we can emerging disease, real time trends. Okay, these things can be can be solved through the AI or machine learning also. For the example, COVID-19 taught AI models new pneumonia signatures in weeks, not years. Okay, so this is one of the examples what we are getting. Next one. From hospital centric care to the now we are going to remote to wearable and home based AI. This is the major shift. That is smartwatch, ECG, SPOT, sleep, HRV we can get instantly. And we are using also smart watch IoT devices. Remote patient monitoring system we can do it. And telehealth plus AI chatbot through AI chatbots we can get the result. AI detects early signals of atrial fibrillation, sleep apnea, heart failure, stress and chronic disease, bring preventive health care to every home. Okay, so these are the new shift in the healthcare systems. Next one, please. From generic drugs to AI designed therapies. Now old drugs delivery is 10 to 15 years. Now AI accelerate molecules discovery, protein folding predictions, AlphaFold, clinical trial simulation, side effect predictions, and huge paradigm shift in pharma and biotech. These are the some examples of the paradigm shift in AI and machine learning algorithm in the domain of healthcare. Next one, please. Next one. From privacy concern. Back slide, please. Back slide. From privacy concern to federated, ethical, and explainable AI. New standards is federated learning. Data stage in the hospitals, differential privacy, model explainability, XAI, algorithmic fairness, reduced biasness, and HIPAA, GDPR, DISA compliance we can. So what will get the impact? AI become trustworthy, transparent, and legal deployable. So these things are the that is privacy concern to federated and ethical explainable AI. So we can diagnose what are the causes and so on to the explainable AI. Okay, that is the major shift. Next one. So summary is that is the old healthcare AI means the rule based siloed data, one big task model in hospital diagnosis, human only decision and static algorithms. Now new health system is next one please. The paradigm shift is next one. New healthcare AI give to data driven learning, multi-modal integrated models. Many models can be integrated and become a hybrid and give the predictive results in the more precision way. Foundation and generative AI, remote digital health, we can capture the remote area in the healthcare system. Human AI, hybrid decision making, continual learning system we can adopt, ethical links level deployment, and precision medicine can be deployable in the new healthcare AI. These are the major shifts of the major shift from machine learning, AI in the healthcare system. Next one, please. Thank you all. Thank you very much for your patience. Any questions from the audience? Any questions from the audience?
Participants, you may ask any questions if you have.
Good evening, sir. Am I audible?
Yes, please.
Good evening,
You may
sir. My
ask.
name is Professor Ashish Sawant,
Okay.
and my question is regarding I'm doing my research inside the same field, sir. But most of the time, the opponent peoples are always saying me, why you are directly taking a data set from Kaggle or any UCI storage
Okay.
for predicting the heart disease condition. Why you are not
Mhm.
collecting directly? It is from the user. But my hurdle is what whenever I'm getting a data from user, so they are not aware about the much more attributes which is a part of my data. So
Okay,
that's
okay.
why I'm
I
getting.
understand. I
Yes,
understand
sir.
your question.
So
Your question
what we are
is
supposed to say about the same thing?
okay. Let us see. Uh, Basically, we are applying the machine learning or deep learning models for the voluminous data, not for the low volume of data. That is the first reason. Okay, is it clear?
Yes, sir. Yes, sir.
And if you go one by one to the persons, that is the traditional approach. You can get the data from the hospitals. If hospital is having the data center to capture the patient, then you can get the data from the hospitals. That is the one way. You cannot get from the Kaggle or the UCI or other repository data, right?
Yes, sir.
So you can give the answer like that. And in India, that is the very difficult. Even I don't think that that is a big hospital having the data center. If they are having the data center, they have the privacy issues. There is a very tough rule in the India to give the human data to the anybody for the research
Yeah, yeah.
because
Actually, the most of the time we are getting the data from foreign countries.
yes, that's true.
Just like a very popular data set is there on Kaggle, which is having a name as a Framingham dataset.
Yes, I know.
But we didn't got any kind of solution for the Indian data repository.
You can ask from the AIMS New Delhi. They can give some data if they are available.
Okay, sir.
Okay, and that is the each and everywhere is the problem in India. You cannot get the data. Uh, It
Yeah.
is it is simple to say you can get from there, but when you go there, they will not give you.
Yes, sir.
That is the main problem, and you are in the learning phase. If you are doing PhD
Yes, sir.
in the AI in healthcare, then you are learning phase. So you are basically what you are doing. You applying the machine learning models. You are applying the deep learning models to get the prediction and so on, right?
Yes, yes, sir.
So when you learn the things, then you can apply for the Indian data base also. So that is not a big thing, I think. If
Okay.
people are asking why you are not getting the one by one person data, that is not a relevant question because you are applying the huge volume data on the deep learning models. You are not working for the low volume of data.
Yes, sir. Thank you.
Oh,
Thank you, sir, for motivating me.
yes, okay.
Thank you, sir.
Any other questions, please, if you have?
Sir, I think there is no more question.
Okay.
Okay. So this is the end of technical session 1. On behalf of the entire Atal FDP team and organizing committee, I extend my heartfelt gratitude to Professor Pramod Kumar Mishra, sir, for delivering an immensely enlightening and forward-looking technical session on paradigm shift in AI and machine learning for healthcare. Sir, you have mentioned how artificial intelligence and machine learning is transforming healthcare and also explained paradigm shifts from rule-based systems to data-driven learning, from simple models to deep and multimodal AI, and from static prediction to personalized real-time care. Together, these shifts are reshaping diagnosis, treatment, and the future of medical practices. You have also explained technological shift in very simpler way using short video too. We are sincerely thankful for your time, your expertise, and the motivation you have infused into today's session. Thank you once again, sir, for enriching our FDP with your vision and knowledge. Thank you so much, sir.
Thank you. Thank you. Thank you very much. So I'm leaving the meeting.
Yes, sir. Thank you, sir.
My voice is audible to all. My voice is audible to all.
Yes, Javed, you are audible.
Okay, thank you, Vijay sir. Thank you so much. Now, dear participants, we are starting our today's session number 8, day 4. It's my privilege to introduce our distinguished resource person for the today's session, Dr. Vijay Kumar Bahut. He is the academician and the inspiring researcher in the field of computer science and engineering. Dr. Vijay sir is currently surveying the assistant professor at the Department of CSE at Netaji Subhas University of Technology, that is NSUT, New Delhi, one of the India leading engineering institute. Since joining NSUT in year of 2021, sir has been contributing through his teaching, research, and academic leadership. Sir academic journey is very impressive. He is completed his MTech and PhD from the prestigious institute Atal Bihari Vajpayee Indian Institute of Technology and Management, Gwalior, an institute of national importance known for its excellence in the computing and the management science. Dr. Vijay sir research expertise covers some most of the interesting areas like modern computer science, computational engineering, computational intelligence, machine learning, image processing. He is the author of more than 20 high quality research papers published in SCI, Scopus, and Web of Science. His notable work include publication in distinguished venues like Expert System with applications, knowledge-based system, applied intelligence in IEEE, transaction on the nanotechnology as well, reflecting the depth and the relevance his research contribution. In addition, his scholarly excellence sir actively contribute the global research community as a peer reviewer for the several top tier journals like SCI, Springer, elsewhere, like that, including the knowledge based system and the expert system with applications, with further demonstrate his expertise and in academia reputations. So today we are welcome Dr. Vijay sir for taking a session and sharing his valuable knowledge in the same domain. Sir, over to you, sir.
Thank you, Dr. Javed, for inviting me for this technical talk in the proposed Atal FDP. Thank you, Dr. Wimby, madam. Both are in touch with me for organizing this talk.
Thank you, sir.
So I'm sharing my screen.
Please, sir.
Is it visible, Javed, sir?
Yes, sir. It's very much visible, sir.
Good evening, all participants. I'm Dr. Vijay Kumar Bohat. Today I'm presenting my topic, image segmentation using novel meta-heuristics. So in this talk, I will cover a very popular nature-inspired meta-heuristic that I've used and got publications in many prestigious journals, Grey Wolf Optimizer, and its application in multi-level thresholding of images. And after getting inspiration from this optimizer, I have also proposed my own nature-inspired algorithm, motivated by the phototropism phenomena of plants, phototropic growth algorithm, PGA. These are the outlines of my presentation. First, we discuss what is image segmentation. Basically, image segmentation, we want the area in the images, the content of the images needs to be separated. An image into its constituent region or objects. Whatsoever the knowledge available in the images, we can extract that particular knowledge. It's a difficult task because of the nature of the image. Sometimes the nature of the image is very simple. It's very easily segmentable. But sometimes the histogram of the image is not easily segmentable. So we have to apply some particular special optimization techniques. Based on the segmentation accuracy, it determines the eventual success or failure of computerized analysis procedures. So if the segmentation procedure or the segmentation accuracy is more, whatsoever the algorithm or the task at hand in the field of image processing, that particular computerized procedures always have better performance. Mathematically, we can present segmentation via thresholding also. For the image segmentation, there are multiple methods. Okay, thresholding is one of the popular method in the field of image segmentation. It's very simple and easy to do. That's why majority of the researchers or the person who works in this particular field go for thresholding for image segmentation. Mathematically, we can present thresholding via this function. Like if the image we can represent in with the help of function g of xy. So if we talk about the pixels, so if the pixel value we are getting from fxy, and if it is greater than a particular threshold, we will mark it as 1. And if it is less than a particular threshold, we will mark it as 0. So this particular function is for single level thresholding. Means in the image, we will decide only one single threshold, and via that threshold, we will divide the image into 2 parts. So our task is to separate the foreground from the background. Like in this image, like the hardware tool is on the table and the histogram is visible. So we can easily see that in the histogram, we can easily find what is the appropriate threshold. Okay, it's very easy to determine that the appropriate threshold by which I can separate the foreground and background into 2 parts is in the middle of the histogram of the image. So if I take the value of t approximately equal to 127 or 128, the resultant image I will get like this, which is given in the lower side of the figure 1. So it's a thresholding example 1. So in this kind of histogram, the segmentation or determination of threshold value is very easy. Like in this example also, it's a figure of thumb image. Okay. So in the original image, there are some impurities or there are some noises. But after doing thresholding, the image on the right hand side is almost clear, and we can easily observe that if we apply algorithm of fingerprint recognition or any other sort of algorithm on the rightmost image, the performance will be much better than the compared of the image which was on the left side. But again, by seeing the threshold, it's easy to determine where is the threshold I need to place. But look at this example. It's a very famous image, Lena image in the field of image processing. And the histogram of the Lena image is available over there. So particularly for this image, it's not easy to determine a single level threshold, which can generate more knowledge or which can enhance the accuracy of any computerized procedure for any sort of task. Okay. So in such cases, we need multi-level thresholding of image. But with the help of single threshold, we're not able to segment the images. We need to divide these images into multiple classes. But currently, the threshold is having multi-modalities. Okay. So depends upon the nature of the image, or depends on the histogram. We have to decide how many thresholds we require so that our foreground or background or the interested object that we are looking for is going to be separated, and we can easily perform our next procedure. Okay, accuracy or any application in the medical field. Like in this image, we suppose we have this threshold histogram, and in this histogram, if I want to divide it into 8 histograms, so these are the 8 thresholds I can apply. And after applying these 8 thresholds, this histogram is divided into 9 classes. Okay, like 0 to 51 is one class, then 52 to 74 one class, 74 and above another class, like in these classes. So when I'm going to give a single pixel value to a single class, so in the resultant image, I'm going to have only 9 colors in the image. And most probably, the region of interest will be very easily clear in the resultant picture after doing the segmentation or multi-level thresholding of images. Mathematically, we can represent multi-level thresholding in this way, like GXY. Okay, so every pixels we are going to divide into. If we have m thresholds, then we are going to have m+1 distinct classes, which are as follows mathematically, like this: C0, C1 up to Cm are the classes. C0 to Cm means it's m+1 classes, and based on m thresholds, we are going to apply. How to decide which threshold is good or where to put the threshold, like in this kind of histogram, like images of diverse natures. Images, the histogram can be of any type. It's basically the intensity levels varied from 0 to 255 or 1 to 256, depends upon the settings we have done. So for finding the quality of thresholds, a very popular criteria, that is Otsu criteria, proposed by scientist Nowaki Otsu, and it's a very popular criteria in the literature for multi-level thresholding of images. This criteria depends on this point, is that if we want to separate the foreground from the background, okay, so whatsoever the classes we are going to have in this particular histogram, those classes variance needs to be maximally separated. So this criteria is also known as maximizing between class variance criteria. Okay, so the equation second proposed that we have to maximize a function which consists of thresholds, like m thresholds. Suppose we want to divide the image into m+1 classes, so we have to find best m thresholds that we are going to place in the image, and with those thresholds we are going to have m+1 distinct classes in the histogram, and we are going to give a different value to each class. so that the image looks like it is segmented. Where T is the vector constitutes the thresholding values, T1 up to Tm. So Ft1 up to Tm is the Otsu function defined as f equals to summation I is equal to 0 to m omega I mu I minus mu square. So in the equation 3, I is equal to 0 to m. So m are the thresholds that we are looking for. For every threshold, we have to basically maximize this particular function. Ab mu I minus mu. So mu is the mean variance of the class, complete class, and mu I is the mean of the individual class. Okay, so we are going to have m+1 classes. So the best placement of the threshold that which gives this value, maximum value of this particular function, is going to are the best thresholds, where omega I is the summation of the probabilities of a particular class. A probability of a particular class means for every gray level. Omega I ka the formula is J is equal to Ti up to Ti plus 1 minus 1. So where the intensity level of one class starts, like in this example, it's for the first class, the intensity level starts from 0 up to 51. Okay. So here in this example, J is 0 up to 51, 52 minus 1, we can say 51, and Pj. Pj is the probability of occurrence of that gray level. How we define the probability of occurrence of gray level? The formula is given in equation 5. Hj is the intensity of that particular level. Like in this diagram we have, suppose we are determining for this gray level. So this is the intensity divided by total number of pixels. TNP stands for total number of pixels. In any image, if we multiply its row and column, the number of rows and number of columns, so we can get the number of pixels in the image. That's how we calculate probability. So overall, Otsu defined one important criteria through which we will put different values of T1 up to Tm, and the values, the combination of vector T1 up to Tm that maximizes this function is the best threshold, multi-level thresholding of multi-level thresholds of a particular image. Up now, as the gray levels varies from 0 to 55, so there will be multiple combinations of thresholds, and we need to find the best one. For that, we require optimization technique, optimization algorithm that will find the best threshold for us. An example is given in the slides like figure 5, original and segmented images. In the original image, a church is a popular image in the field of image segmentation, church image. And in the next image, if we select threshold 5, then this image will be divided into 6 different classes. So segmented image covering all the important knowledge of the image, and you can easily get have more knowledge in the segmented image, like the different intensity of sky, the light different intensity that is visible in this image. The door area is completely black out in the segmented image because it's come in a single range. So the right hand side image have more knowledge as compared to the left hand image because of the less number of classes. So computerized processor can easily work well in the segmented image. Now, how we can optimize find the best thresholds for a particular given image. So for that, we have there are multiple algorithms available in the literature. Okay, but this particular algorithm, Gray Wolf Optimizer, is one of the population-based meta-heuristic and is one of the popular algorithm in the field of meta-heuristics. Before discussing this algorithm, let me discuss why it is more popular, why people are using it. Because see, there are currently in this world, there are more than 500 or 1,000 nature spat algorithm daily in every journals. People are communicating papers and people are getting published their own phenomena, nature spat phenomena. But this particular algorithm is proposed in 2014, and the framework and the equation involved in this algorithm is particularly very easy. One of the more important quality that a researcher finds it very easy to use that algorithm is that number of tuning parameters is almost none. There is one tuning parameter, although You can say it is a tuning parameter, or you can say it's a constant. But in other algorithms, like popular nature span heuristics like PSO, genetic algorithm, number of tuning parameters are more. And their equations are not that much simple as of this particular nature span heuristics. Okay. So this algorithm is proposed by Professor Syed Ali Mirza Lili in 2014. This algorithm simulates the leadership hierarchy and hunting mechanism of grey wolves. Basically, grey wolves are considered as apex predators, which are at top of the food chain, and they prefer to live in a pack or in group, contains 5 to 12 members, and they have a very strict social hierarchy. I mean, the hierarchy is that alpha wolf is the leader wolf of all the pack. All the wolves will submit themselves to alpha. They will follow the decision of the alpha. Whatsoever the alpha takes the decision, alpha is known for taking hunting level decisions and where the pack lives. Such important decisions is being taken by the alpha wolf. Second wolf in the hierarchy is beta wolf, followed by delta and omega wolf. Okay, so as the hierarchy goes down, the number of wolves in that particular criteria increases, but at the leadership position, there are only few wolves. The second level is beta wolf. Beta are the subordinate, which helps alpha in decision making. The beta wolf can either be male or female, and it's considered the best candidate to be alpha when the current alpha passes away or becomes very old. The beta reinforces the alpha's command throughout the pack and gives the feedback to alpha wolf. The next is a delta wolf. Delta wolf is not uh, a weak wolf in the category, but it's a third in the hierarchy, but is performing important duties like scouting, are responsible for watching the boundaries of the territory, sentinels taking care of elders, hunters, and is also caretaker of ill and the children's. The fourth and lowest level is omega, which is the follower of all the wolves. But the quality of this particular grey wolf is that they don't want to lose omega. If the omega is not in the hierarchy, in the top three hierarchies, but it's an important part of the grey wolf pack. I mean, the social hierarchy, alpha, beta, and delta. When the Professor Mirza Lili is making this algorithm, so he has given weightage to alpha, beta, and delta, and not considered omega wolf in the algorithm, mainly equations algorithms. Suppose we generate population size in this particular optimized algorithm 30. So the first three wolves that are going to have the best fitness are going to be alpha, beta, and delta. Rest of the solutions will be considered as omega. It means 27 wolves are going to be considered as omega. The best fitness will be alpha, second best will be beta, third best will be delta wolf. That's how the hierarchy of grey wolf has been used in the grey wolf optimizer. It's very easy. The second important mechanism in the grey wolf is encircling the prey. First is social hierarchy is very important. Second important phenomenon is their hunting mechanism. How the grey wolf hunts. I mean, in the diagram we can see in the slide is that the prey is of size double as compared to the wolf. Means a single wolf cannot outperform its prey. That's why this particular class hunts in group or pack, because a single wolf cannot outperform the prey. Outperform will easily throw the wolf away through its horn, and can move away. So it's responsibility of the wolves that they make some group and hunt in a group. Their hunting mechanism is also very interesting, how they hunt. So first, during the hunting, the grey wolves encircle the prey. I mean, when they see the prey, they simply don't attack the prey. First, they encircle it, and they move along with the prey. Okay, and they move along with the prey for a while. It's kind of they are mentally harassing the prey, and when they come to know that prey gives up, then they shrink the circle, and then they attack. When the prey mentally gives up, because the prey, if the prey will show some phenomena, show some daring among in front of wolves, prey can easily break the circle and can run away. So grey wolves are not in any hurry. They just encircle the prey and they moves with the prey and they shrink the circle with lapse of time. This phenomena is very important in this phenomena motivates the author to use it in the optimization algorithm. Okay. First is the social hierarchy, that is alpha, beta, and delta wolves. Second is this encircling mechanism, which is encircle the prey, and after encircling the prey, then you shrink the circle. Don't directly attack the prey. Shrink the circle with lapse of time, and then attack the prey. So this phenomena gives important equations as in the field of optimization algorithms, and provides the phenomena exploration, initially exploration of the search space, and then later on exploitation of the best solutions. Of how the mathematical model of encircling behavior is presented in the following equations. Like in the equation, this d is equals to vector d is equal to vector c multiplied by xpt minus xt. Ab, a solution of any problem will be a vector. Like in the nature spider algorithm, the first thing is that you initiate random solutions between the upper bound and lower bound of the images. For example, like in these equations we have, okay, suppose the objective function for which we need to optimize, or we need to find the best value of it. We need to minimize the given objective function, x1 square plus x2 square. So there are infinite solution of this particular problem, because x1 and x2 are lies between minus 10 and 10. Minus 10 is the lower bound and 10 is the upper bound of those two variables. And they can have infinite values between minus 10 to 10. But we need to find the value for which this particular function have minimum. And we know through our knowledge that it's 0, 0. The solution is 0, 0. If we put x1 0 and x2 0, the fx will be 0 and it's the minimum one. Otherwise, there will be some value because it's x1 square or x2 square. But to find a procedure through, not every real world problem is that simple and easily determined. So between the lower bound and upper bound, we initiate many random solutions as a population of wolves. So suppose I want to initiate 10 solutions. So I will have 10 different vectors. Each consists of two elements representing x1 and x2. And they will be lies randomly between minus 10 to 10. So I can say that I have 10 grey wolves. Okay. Now for every grey wolf, like I have 10 grey wolves, for every grey wolf, I will minus its position from xpt. Now this xpt is the position of the prey, and multiplied with c. C is random number between is equal to 2 into r2. R2 is a random number between 0 to 1. Okay. What this equation is going to give us, that the distance between the solution and the prey, okay, distance between the solution and the prey, and c is multiplied, which is basically 2 into random number, is going to give us stochastic phenomena in the equation. Because if we directly subtract the position of the solution from the prey position, it's a simple distance. But these optimization algorithms works on the stochastic phenomena. So C is there to introduce stochastic phenomena in the algorithm. Now, in the real world, we know what is prey, but while solving a optimization problem, we don't know what is prey. So in this algorithm, prey is considered as alpha, beta, and delta wolves. When we are going to initialize randomly 10 solutions, okay, so we'll calculate the fitness of those solutions by using this particular function or whatever the objective function we have. Like in this algorithm, in this slide, we have x1 square plus x2 square. Suppose I initiate 10 solutions. So for every solution, I will put its value into x1 square plus x2 square. I will calculate its value. That is fitness evaluation. So after fitness evaluation, I will have the fitness value of all the solutions or all the grey wolves, I can say. I have I have fitness values of them, and the best fitness value means the function criteria is the minimization. So the least fitness value is the best wolf, that is alpha. Then second least is beta. Third least is delta. So the distance d is basically calculated with respect to alpha, beta, and delta. So for every solution, I will calculate D 3 times with respect to alpha, with respect to beta, with respect to delta. And the next position of the solution in the next iteration, because these algorithms works in iterative manner. Means initially you will have a random population, but with every iteration, those random population moves towards the best solution so found so far, doing the exploration and exploitation of the search space, and will try to move towards the optimal value or optima, we can say. So we'll replace xp with x alpha, with x beta, with x delta. And then again in the next equation, we replace with xp again as x alpha, x beta, x delta, minus a dot d. A is again a random number. Okay, depends upon 2a r1 minus a. R1 is random number between 0 to 1. And small a is a value which initially was 2 in the starting of the iterations, and later on it becomes 0. Why is small is decreasing from 2 to 0? The reason is that because we need to shrink the circle, because how the grey wolves attack the prey is like they initially encircle it. So for encircling, these equations are d and xt plus 1 is responsible. And to introduce the shrinking mechanism, shrinking circle behavior, this small a is introduced, which is initially it's large, but with lapse of iteration, it will lose its value towards 0. And this will introduce a shrinking circle mechanism in the grey wolf equation. So in the calculating this capital A, small a has been used, which shrinks the circle. So these two equations, with the help of these two equations, the author is able to achieve the hunting mechanism behavior of the grey wolves. So the algorithm is very simple. Okay. The hunting operation is usually guided by the alpha, beta, and delta. And the first three solutions are saved, and other agents are obliged to update their positions according to the position of the best three agents, that is alpha, beta, and delta wolves. These are the equations. Every solution will update its value with respect to x alpha, x beta, and x delta. And then it calculates next position with respect to alpha, beta, and delta. And the next position of the solution is going to be x1 plus x2 plus x3 divided by 3. It's average value. So in mathematically, in this diagram, it has been shown that the solution of the wolf is presented through the pink circle. Alpha, beta, delta is given through this blue, yellow, and violet. Okay, and through the averaging, we have determined one particular value. So estimated position of the prey is determined as yellow by taking the average x1, x2, x3. Okay, alpha is blue, beta is violet, and delta is green. So the average of 3 will make this value move toward this particular circle. So in this way, every solution, in every iteration, the solution or the bulls will calculate their next position. And iteratively, the agents move in the grey wolves, moves in the search space, and they move towards the optimal solution. Of how exploration and exploitation phenomena is introduced in this particular algorithm. Exploration and exploitation phenomena is very important phenomena in every optimization algorithm, because see, you don't know where the original, the intended solution lies in the search space. Search space is very big. As the technology is increasing, the dimension of the problem is increasing. We are right now we are solving, like we are living in the age of generative AI. So generative AI is basically, we can say, neural network. That is a very well-trained neural network. But if you want to optimize that neural network for its performance, if you come to know how many parameters it's going to have large dimensions, large number of nodes the network have, and to find the optimal values of weights and biases of this variable. So dimension is in thousands or in lakhs for a generative AI network. So the dimension of the problems are very large. That's why we require algorithms that can do explore well the search space and exploit the best found solution so far. So Grey Wolf finished the hunt by attacking the prey when it stopped moving. The vector A is a random value in the interval between -2 to A, because we have seen the equation of it. So when A is decreased from 2 to 0 over the course of iteration, we can say it's doing the exploitation of the search space, because the circle that the granules have made around the brace shrinking with the lapse of iterations. So with the lapse of iterations, we can say exploration is losing and exploitation is increasing. So when mod of A is less than 1, the wolves attack towards the prey, which represents exploitation process. And when mod of A is greater than 1, and mod of A is greater than 1, when A is the small is 2, and when small is decreasing towards 0, then we can say its exploitation starts. Exploration fades off and exploitation comes in the picture. When to explore, when to exploit, there is no clear direction available in the literature. It has been said said by the previous researchers that initially we have initialized the solution randomly. Okay, so initially when we have initialized the solution randomly, so we need to explore the search space, do the exploration. But with the lapse of iterations, starts exploiting the best solution found. So these two phenomena has been well taken care by the GWO equations, and that's why the GWO outperforms other algorithms in various research problems. Interesting that algorithms I can summarize. The GW algorithm pseudocode is available in the picture. How we start? Okay, so as I've started in the starting of the lecture, this talk, I've said that the GW doesn't have too many tuning parameters. Okay, so initially we decide the number of population size, that is n. Parameter A. A parameter A is not a tuning parameter. In the research paper of GWO, it has been given that its value linearly decreasing from 2 to 0. So it's kind of fixed. Coefficient vector A is completely dependent upon A and random number. So again, it's not a tuning parameter. C is again 2 into R, random number, and the maximum number of iterations, max IT. So ethically, we can say that there is no tuning parameters in the Grey-Wolf optimization algorithm. Although some researchers have said that A is kind of tuning algorithm, you can tune it by searching different ranges of small a for experimental purpose. That can give you a new trade-off between exploration and exploitation. But those who want to directly utilize GWO for solving a real-world problem, they can directly use this setting, small a, and so that it does not have any tuning parameter. After setting these initial values, then you can go for counter initialization of iterations t is equal to 0, and then we can start our main loop, in which first we randomly generate the initial population, depends upon the size n, and evaluate the fitness of each search agent or each gray wolf, we can say. After evaluating the fitness of the each gray wolves, we go for the assign the values of first, second, and third best solution, x alpha, x beta, and x delta, respectively. Now, after getting x alpha, x beta, x delta, our job starts that for every gray wolf, we have to calculate its next position with respect to alpha, beta, and delta, and then take average, x1 plus x2 plus x3 divided by 3. So this loop starts from line 8 to 15, or we can say 8 to 16. Is basically every agent is just updating their equations, and the value of small is kept on decreasing with the lapse of iterations. So initially, the agents explore the search space, they try to find the best solution found so far, and with the lapse of iterations, the small a decreases towards 0, and they start exploiting the best agents and try to search near the best agents. And ultimately, when the all iterations are over, then we produce the best solution found so far, that is x alpha, in the last iteration. So we return back the last after the last iteration, the best solution found so far, x alpha, as the solution of the problem. Okay. Now in the literature, example is given in the slide. It's the same fitness function, x1 square plus x2 square. Suppose I generate 5 different gray wolves. 0.9274, 3.7813. First dimension is this, second x1 value is this, and x2 value is this. leftmost is x1, rightmost is x2. And then for these 5 rules, I can evaluate their fitness by putting their values into x1 square plus x2 square. So that will be my fitness: 15.15, 42.84, 54, 77, 52. Okay. But after 5 iterations, if I set parameter a is equal to 2, and I randomly decide R1, R2 is random, then you can say just after 5 iterations, the first solution is 15.15, it becomes 9.91. The second solution is 42.84, it becomes 9.686. So it's a huge optimization. 54 becomes 9.4, that's again huge. And 77 becomes 17.50. 52 becomes 16.97. So all the gray wolves, just after 5 iterations, are observing that they are moving towards the optimal solution. An optimal solution is 0. We know x1 square plus x2 square, the minimum solution is 0, 0. So if we increase the iteration, then definitely they will work upon, and they will, after some 100 or 200 iterations, they will land to the solution 0, 0. Okay. So that's how this GW algorithm works. And now we move to its real world applications of this optimization algorithms, where we apply these optimization algorithms and how we apply. Okay. So for application of meta heuristics, like in the field of medical healthcare or in any other field, because these algorithms are very much, we can say, they are like black boxes. Black boxes means how these algorithms are working is not much known to us. Much known to us means we can decide that with small a exploration initially and later on exploitation. But in the mean, from the first iteration to last iteration, we majorly depends upon the random numbers, the stochastic phenomena and the algorithms. So how things goes in between, from between the first iteration and last iteration, is not in our control. But this setup gives us near optimal solution majority of the time. Up to solve these algorithms, with these algorithms, we can solve many real world problems. The literature is full of such applications of it. One of the research that I've done, that I've utilized these algorithms in face image super resolution. Okay. I will discuss what is face image super resolution with the example. Like in this image, the left hand side, we have images of the facial images of the person and the high quality image. And the right hand side, we have the facial images of the person, the same person, but with low quality of image. Okay. Up in the real world, still we have low quality images, multiple times, like in surveillance, or some old camera has been utilized for capturing the pictures, or the angle is not good. So, or because of the noise in the images, like in the currently in Delhi, we all know hazing is there, fog and smog is there. So the surveillance camera is not able to clear high resolution pictures. So we need techniques that will artificially increase the resolution of the images. They makes them more clear. So we are much interested in the left hand side of the images rather than right hand side of the image. Okay. Of how to, if the input is this image, like the images given in set P, if these images are input to us, what magic we need to do to get the images from the right hand side. So face image super resolution is one of the technique through which we do this kind of magic with the help of training images, and we try to generate high resolution images, that is HR face image. Okay. Now how this setup is placed, I will explain. Initially, we have some training images. For those training images, we have their low resolution images as well as their high resolution images. So there's a pair of images we have. Whatsoever the training image we have their corresponding low resolution as well as their corresponding high resolution images. Our input is a new low resolution face, like given in this diagram. Our input is low resolution face. Now what we'll try to do is that we try to generate this image with the help of LR training phases. How to generate an image in terms of other images. So for this, there's a mathematical equation. We can say the objective function of this particular problem, phase super resolution FSR problem. Applying in this equation, we have ILRC, which is the input image. Okay, this is the input image we have. Input low resolution image. L stands for low resolution. RC is row and column. Now these P, L, and RC are the training images of low resolution, and there are n number of training images. So n, with the help of all training images, we try to create an image that is equal to the low resolution image, input low resolution image. So we multiply a weight vector 0.1, 0.001, 0.02 to every input, to every training image. And with the help of all training images, we create a single image and we separate it with the original input image. And we'll try to minimize this function as equal to 0. Because if we are able to get 0 from this function, it means that we find the weights to which we apply these weights to training images. And with the help of all training images, we're able to create an input image. Because the subtraction is 0, it means that identical images are on the both sides. Okay. So we need to find, our job is to find the weights in such a way that with the help of all training images, we are able to create a input low resolution image. The constraint is given that summation of all the weight is equal to 1 because we have to create only one image. So the summation of all the weights is equals to 1. I mean, this diagram, suppose I am able to find W1, W2, Wn, a combination of vectors. Their values lies between 0 to 1. Okay. And the summation of all weight vectors is equal to 1. So if I are able to find those weight vector of the LR training phases, the minimum, I just try to do minimize this particular one, minimize this function. So the best weight vector, if I'm having it, I will apply this same best weight vector to the HR images. And if I apply to the HR images, the resultant HR phase of this input LR phase, I'm able to get. So this is how low resolution image can be created through a position, a learning based facial, we can say facial super resolution approach. We can have function in which we, with the help of training phases, low resolution training phases and their pair of high resolution training phases, we're able to create a resultant HR phase. Means a completely new low resolution image can be we can come up with a HR phase. So I have utilized multiple nature span algorithms for solving this particular phenomena. In that particular algorithms, we have taken some standard data set, and with the help of the standard data set, we compared the performance of different algorithms. Like in this diagram, the last row is the ground truth, that is original HR image, original high resolution image, and different algorithms like PSO, differential evolutionary algorithm, wheel optimization, GWO. All these algorithms have created the phases, and we can easily observe that the best algorithm in this particular category is a GWO based variant, which almost find the best weights, and with the help of those best weights, we are able to come up with the original image which is very close to original high resolution image. Okay. PSO performance is very poor, differential evolutionary algorithm is very poor. GSS stands for gravitational search algorithm, its performance is not up to the mark. But GW and a variant of GW is performing really good in this particular algorithm. And the reason behind its performance is the exploration and exploitation phenomena of this algorithm that we have seen, the equations, and easy application of this algorithm. Okay. Now, those images with the eyes, we can observe that the generated super resolution images are good by the GWO. With the help of some mathematical metrics that has been testified, the same phenomena is testified, like peak signal to noise ratio and structure similarity index, which lies between 0 to 1. So the best numbers we're able to get by the GW variant, FSR GW. Or GW is also the topper among the basic nature span algorithms. Okay. Anybody got any doubt till now? I asked the participants, like we're moving to the next algorithm we have. Till now in the up to Greyfulf optimizer. If anybody have any question, we can discuss it. And then again, we move to the next algorithm. Okay, till now, so we have discussed Greyfulf optimizer, a very popular nature-inspired meta heuristics, and two applications of it. One in multi-level thresholding of images, plus one in facial image super resolution. Now next is phototropic growth algorithm. This particular optimization algorithm has been proposed by me in 2025. I think the paper has been published in a knowledge-based system in May 2025. Okay. It's a very prestigious, reputed journal of Elsevier publishers, and the algorithm takes the paper takes more than 1.5 year in the communication phase, and finally it was published in this year only. Okay, so in this algorithm, like I've studied many nature-inspired algorithm like genetic algorithm, differential evolutionary algorithm, Greyfulf optimizer. So me and my some co-authors were looking for some nature-inspired phenomena through which we can uh, come up with a meta heuristics that performs better, that have good exploration phenomena, a very good exploitation phenomena, and we're looking for some inspiration in the nature. So we have found one motivation from the nature is that the movement of plant cells towards light source. We often see that some plants are bent towards one side, some plants are bending towards one side. It's all because leaves require lights, and they have some phototropic mechanism through which they elongate towards the light. And if you study the hormone changes and the oxygen hormone and all those things, you will find the inspiration for a particular nature SPAD algorithm. So I will explain those inspirations, and then we'll discuss the mathematical equations. Okay. Now these are the important terms in this particular field. We all know what is cells. In the human body, we have cells. In the plants, they have cells. Cells are the basic building block of nature, we can say, of every biological species. Cells are the building blocks of that particular species. So everybody having cells, cells are very much useful in terms of growth. Whenever we fight some many diseases, we lose cells and we generate new cells when we are very healthy. So plants also have cells. So in this newly proposed algorithms, we have cells as solution agents. Like in Greyfulf optimization algorithms, they have Greyfulfs as the solution agents. We have plant cells as solution agents. As the main motivational phenomena is that light. So light intensity we have considered it as fitness function. Okay. Few important terms that cell division, because with lapse of time, as we grow, like plant grows, and how the plant grows or we grows is that we generate new cells. So there's a process called mitosis in the plants. Through mitosis, a cell generates its own copies. Okay, a cell try to generate its own copy. First copy, second copy. So that's how the daughter cells are generated, and we can say it's mitosis phenomena. Sometimes it's cell elongation because of the nature, like in the morning light is good, afternoon light is good, in the evening light is not good. So based on the light source, the cells are going to elongate towards one side. Then there is a term called oxygen distribution. Oxygen distribution is related to the oxygen is basically a plant hormone. Okay, it's a plant hormone, and based on the light, it changes. Cell vicinity and mutational operators. Mutational is an old term in genetic algorithm. This term is also there. And in the real world, mutational operator is there because see, as the time changes, mutation is getting done. Okay, like in the human body changes a lot with lapse of time. Some species are completely wiped off from this world because they are not able to do a proper mutation or adaptation in this particular world. As a human species, we have adopted ourselves for this particular nature. Few species like dinosaurs and all other previous species, they're not able to adopt with lapse of time. So whatsoever we can say, they have not done the proper mutation for the survival of their species. And the humans and the current species, they have done their mutation. Some of the species from the documentaries of WHO, we comes to know that they are on the verge of collapsing. After some years, they will not be in the world, like black bugs or some other species, because they are not able to adapt to the current environment. Or in the scientific term, we can say whatsoever the adaptation, the mutation, the changes in their cell or in the body, they're not able to do that thing. That's why they are on the verge of the species will get wiped off in few times in the upcoming times. Cell vicinity means how the cells are closing to each other. So based on these terms and phenomena, the algorithm have been made. Okay, of how the algorithm works. So when a plant is facing a sunlight, so there will be 2 points of the plant. One side is facing the light a lot and other side is in shadow. So at a point of time when the plant is facing sunlight or the light source, there is light region cells, there is shaded region cells. Just like in the previous gray wolf optimization algorithms, initially we generate population of random size. Okay, initially we generate a population randomly. Similarly in PGA, we will generate population randomly, and then after generating a population randomly, we will divide into 2 parts: light region part and the shaded region part. To know how many agents will be in light and how many agents are in S, so we calculate one number called NL. N is the population size, so we C1 C2 minus C1 into R1. R is random number. So with this, C1 and C2 is a constant. It's 0.4 and 0.5. Their exact values given in the paper. Why we have got this value through some experiments. So almost 40% of the cells will become light region cells, and rest of the cells, like with the equation 3, NS equals to N minus NL. So the last 60% cells will become shaded cells, shade region cells. So this is basic. We have divided the population into 2 parts: light region cells and shaded region cells. Okay, XL and XS. In GW, there is only one population, that is X. We divide that X into XL and XS. The first 40% will become XL. The next 60% will XS. It's not exactly 40-60, but it's approximately in this range. It depends upon the R1, what is random value. Depends upon that 34% will be light region, 66% will become shade, and in this way things goes on. So that's how we do the initialization of population in the PGA. After initialization, we have 2 phases. Okay, phase 1 and phase 2. Phase 1 is mitosis. Mitosis means generation of daughter cell. I have explained in my initial point in the presentation of the algorithm is that we develop, as we grow with time, we develop new cells in our body. If we are not able to develop new cells in our body, we might be collapse. Okay. So like parents, plants, they want to grow, so they will generate new cell. Okay. But like every species, like human body, with lapse of time, our cell generation capacity is not good, because we know we age. Why we are aging? Why our skin is not tight as always? Because the kind of cells generation capacity, that is not good with us. With lapse of time, we will lose that capacity. Similarly with plant, they also age. Like every biological species, they age. And with age, they are losing their capacity of new cell generation. Okay. So the first equation that we have introduced in this algorithm is alpha exponential decay. Equation 5 and 6, you can say it's an exponential decay equation. Alpha is equal to e to the power minus t by t, where t, small t is current iteration and capital T is the total number of iterations. So with lapse of time, alpha is decaying. And this alpha introduces decay of the power in generating cells. So with the speed, in the initial phases of the algorithm, the cell generation capacity is at the maximum. And when we are slowing down, when we are losing the iterations with lapse of time, that alpha will decrease exponentially and will make the phenomena, the real world phenomena, that is plants are losing their cell generation capacity, the algorithm will lose its cell generation capacity. This phenomena will result in increase in exploitation of the solutions found so far in the later phases. With the help of alpha, we have mathematically modeled alpha in this way that we are going to have exploitation in the later iteration. That is why how we mathematically model alpha. Of alpha we have defined. So in phase 1, we have we decide the mitotic division on light region cells. So we have different equations for XL cells and we have different equations for XS cells. For light region cells, there will be two, like in the equation 7, we have seen that parent cell goes on the mitosis phase and daughter cell 1 and daughter cell 2 generated. So every solution will create two different solutions. So in this equation 9, you can see XL new 1 and equation 13, you can see XL new 2. Every solution will generate two new solutions. Like in GWO, they are moving in the search space with respect to X alpha, X beta, X delta. In this algorithm, all the light region cells, they will generate two new positions for them, two new cells. They give birth to two daughter cells, every cell. What are the phenomena? So first is mutation. To mathematically model the mutation, we have used equation 9. In equation 9, you can see we have used XRAND first, means a randomly any solution will be picked in the population, plus alpha, beta, and R2. So alpha is basically exponential decay. Beta is a number, a vector, which can have only two values, -1 and +1. It cannot have any other value. It's a discrete variable, which can have only two values, -1 and +1. And R2 is a random number. So beta is -1 +1 is to search in both directions, like in positive direction, negative directions. So the algorithms can move in freely in the search space and in both the directions. R2 is a random number. The first is XRAND minus XILT. XRAND is a randomly selected solution. XILT is ith solution for which you are looking for the new, you're generating a daughter cell. Plus alpha, beta, R3, again, alpha is exponential decay, beta is for bidirectional changes, R3 is random number. Then we introduce also give weightage to XIL best. XIL best stands for the best solution in light region cell. We also give emphasis that within the mutation, the best solution also participate. So random cells is also there in the equation 9. Best cell, we are also emphasizing on it. So with the help of it, we are able to explore in the initial phases because alpha value is going to be large. But with lapse of time, when alpha is going to exponentially decay, this equation also results in exploitation. So with the equation 9, we are able to generate the first daughter cell. For the next daughter cell, we apply auxin redistribution operator. Basically, auxin is a plant growth hormone. How this hormone works? This hormone works basically. This hormone is basically work for the survival of the species. Okay. So first in the equation 10, we calculate a difference between the best light cell and the solution, the current solution for which we are looking for the value of the second daughter cell. First we calculate delta x, the distance between them. Then we apply alpha R4 to this delta x in the equation 10. Why we are applying alpha R4? Alpha is basically stochastic. We are introducing exponential decay in this delta also. Initially, the alpha is going to be very high. Later on, alpha will be very less. The same phenomena of the cell generation we also introduce over here. R4 is a random number, but its equation is given by equation 14. 2 rand, 2 asterisk rand minus 1. Rand is a random number between 0 to 1. So R4 lies between -2 to 2. Okay, R4 lies between -1 to 1. -1 to 1. So again, it's bidirectional nature. So it's provides stochastic phenomena in the equation. Exact calculation we are not doing. We're providing stochastic phenomena by introducing R4. And with the help of equation 11 and equation 12 is the expansion of delta x. We've simply put the value of equation 10 in 11, we get equation 12. So XL nu 2 is equals to XILT plus delta x mod. So alpha R4 XIL best minus XILT. So with the help of this, we get the value of this particular one, we can say the new daughter cell, the second daughter cell. So in phase 1 of mitosis, every solution, or we can say every light cell, will generate 2 new cells. So there are 10 solutions. So every 10 solution, we will have 2 solutions. So there will be 30 solutions. And all 30 solutions we will store in the population, ongoing population. So we can say from 10 we become 30. But later on we will pick best 10 solutions. We will not increase the population size more than 10. We will calculate the fitness of all the solutions and we pick the best one. So this is how the movement of the cells of the light region cells. Second, we have mitotic division on shaded region cells. For the shaded region cells, the equations are not complicated because see, for the light region cells, because there are, we can say, they're good. They are showing more phenomena as compared to shaded region cells, because for getting more and more lights, those cells have different. They have auxiliary distribution. They have mutations. Shaded region cells, they don't have much movements. Okay, so again, like mitotic division, they produce 2 daughter cells, cell 1 and cell 2. So excess new 1 and excess new 2 they will generate. To mathematically model their new generation, so we in the first cell, first daughter cell generated by the shaded region is almost similar to the mitotic division of XL light shaded light region cells. Is that we take a random number, take a random X, take a random cell, calculate its distance from XIST, and then apply alpha beta R5. R5 is again a random number, 2 rand minus 1. For XS nu T, so we take mutation into consideration. Okay, how we take mutation into consideration? We can say we consider a light region cell, which is comparatively better than the shaded region cell. They have more movements in them. So XL rand means we consider randomly a light region cell, alpha beta R6, and then XL best, the best value of XL region cells. We take them and we subtract the value of it, and then we apply the stochastic phenomena induced by alpha, beta, and R6, and then we add this particular distance to the XL rand. So this provides a new exploration of the search space. Okay, and it's also denote the mutation phenomena also in shaded region cells. It means shaded region cells are also trying to move towards the light region cell. That phenomenon is also covered through equation 16. Equation 15 is completely playing in the shaded region cell, but in equation 16, the shaded region cell is also moving towards the light region cells. So that phenomenon is also covered in the mitotic division. And then next we have cell elongation. Okay, and cell elongation means as we see in the initial diagram, the plants bend towards the light source, the source of light. Okay. That's how the new position of a new position is created. So how they will bend? What are the phenomena that will utilize for the bending? So first we calculate curvature. That they will curvature. They will have a curvature. So we calculate a value of curvature, and the mathematical equation we have made is that with the help of beta, beta is for bidirectional direction, that is -1 or 1, two values it can achieve, multiply by alpha minus mean fitness XL upon best fitness X. Means जो भी mean fitness of the light region cells divided by the best fitness found so far. We separate this value to the alpha and then we multiply it to beta. Through this setup, through this equation, we try to calculate the curvature. And then with this curvature, we calculate the factor of curvature, FOC. FOC is again curvature multiplied by random number R7. And then this vector multiplied by with xit minus x best. For every solution, we calculate this FOC. And then FOC, after calculating FOC, we also calculate cell vicinity. Cell vicinity says that it's take kinds of average to the near cells, xit plus xi plus 1t divided by 2. And then we also multiply alpha, beta, and a random number to it. So we also emphasize on the nearby cells. What is the position of the nearby cells? Okay. So with the help of equations 17, 18, and 90, we have three values: curvature, which is utilized in FOC, factor of curvature, and then cell vicinity. So factor of curvature plus cell vicinity plus its current position. If we add them, it becomes a new position. So equation 20, we put the values of FOC and cell vicinity, it becomes equation 21. Okay. Equation 21 is not any different equation. It's basically FOC. Equation 18 has been put in equation 20 and equation 19 has been expanded in the equation 21. So we also get a new position of every solution via cell elongation phase. So what happens? What has been done till now? Okay. So till now, we have divided the population into two parts. Okay. We have divided the population into two parts. That is light region cells and shaded region cells. We consider light region cells are having more fitness than compared to shaded region cells. And then we generate two daughter cell for each cell. Okay. Also, for every cell, we will have a new value, new solution will be created through the cell elongation phase. This is also applicable for every cell. Okay, so overall, what we can say, like initially we are going to have 10 cells. So after phase 1, 10 cells will result in 20 more cells, 30 cells. And after phase 2, those 10 cells will generate 10 more cells. So total 40 cells will be there after phase 1 and phase 2. And then we calculate the fitness and we consider the best 10 cells in the next iteration. We keep the best 10 cells. Okay. So we can summarize this algorithm, the phototropic growth algorithm. Like first we generate population of cells X. We calculate the maximum number of function evaluation, max FE, or we can say maximum number of iterations we decide. Then total number of cells equals to N, maximum number of iterations T. And then our output is best solution X best. This is our input. Population we require, the stopping criteria, maximum number of iterations, maximum functional evaluations we require, total number of cells, how many population size is there that we require. After this, we start the initialization. We initialize cell X, different number of cells we will generate. We will set FE initially equal to 0, iteration is equal to 0, we can say. We evaluate fitness for each cell. And after evaluating fitness, we increment function evaluation by 1. Function evaluation means how many times you call the fitness function. Okay. After evaluating the fitness values of each cell, we will say the best solution. Set the best solution as X best. Okay. And then we divide the population into two groups, light region cells and shaded region cells, using equation 1 to 4 that I've shown in the slides. The respective size will be NL and NS. And then again find the best solutions for group X best L and X best S. Among the group, we find the overall X best, the best of light region cells and best of shaded region cells. We initiate the iteration counter T is equal to 0. And then we start the loops. We start the phases. First, we calculate alpha. Then for all the light region cells, from line number 9 to line number 10, line number 11, we calculate two daughter cells. Okay, apply the mutation operator, create first daughter cell, apply the auxiliary distribution operator, create the second daughter cell. Then merge both new cells into population X. Okay. Then for the shaded region cells, for I is equal to 1 to ns, create again two daughter cells using the mutation operator and using the auxiliary and redistribution operator of shaded region cells using equation 15 and equation 16. This will again generate two cells for every solution. Insert those new cells generated into population X. After that, for I is equal to 1 to and 2, create a new cell using equation 21, which is the factor of curvature equation. Okay. So again, all the n cells generate a new solution. Merge the new cells into population X. Evaluate the fitness of all cells that we have generated so far. Select the best n cells as new population, and then repeat the thing iteratively. So in every iterations, the new cells keeps on generating, and then we calculate the fitness of them, we take the movements, and when the fitness evaluations are over or the iterations are over, we report the X best solution found so far. That's how the algorithm works. And the results in this algorithm, we have found the results. I have the paper with me. PGA paper. I can show the results. Like I've compared with these set of algorithms, a large number of nature-inspired algorithms. And in terms of complexity, the complexity is up to the standard. It's not worst. It's equal to other competitive algorithms like Whale optimization or sine cosine optimization. And the results are also good. We have compared on CEC 2017 and CEC 2020 functions. And both set of functions, we are able to achieve rank 1, sometimes rank 4. Overall, the performance is that we are analyzing our results and we are outperforming other algorithms in majority of the comparisons. Like these are the convergence curve, and we can easily observe the exploration exploitation phenomenon of PGA is better than in majority of the functions better than other algorithms. The red one is denoting holotropic growth algorithm, and the other color curves are denoting other algorithms. We also test these algorithms on engineering problems, and we have found good results in engineering problems also. Okay. So now this algorithm is newly proposed algorithms and is available to use, and its application. It's not yet explored a lot in the nature-inspired algorithm or meta-heuristic society. So I request the researchers, the MATLAB code of this algorithm is available in MATLAB Central. Okay. You will write phototropic growth algorithm MATLAB code. So it's available freely available in MATLAB Central. You can download it and you can apply this algorithm in different real world problems. And you can check how it is performing. And we found that it is not performing well, you can modify it. If you understand the equation, you understand the thing, the tuning, the equations which is the performance of PGA depends upon, highly dependent on, you can perform changes in those equations and you can make PGA works better for your selected optimization problem. Okay. So this is in the conclusion, I can say that multi-level threshold of images requires an optimization algorithm that can deal with the problem of stagnation. Phase superposition problem can also be solved using nature-inspired meta-heuristic. With the new formulation of objective function, we can have better constructed images. Thank you all. Thank you all. Anybody have any doubt? I am ready to give the answer of their questions. I think one question, sir, weight calculation for low precision images, how to calculate? Okay. So see, weight calculation means we have low resolution images. Okay. And for those low resolution images, you have corresponding high resolution images. How the weights will be calculated? So we don't have any clue how the weights will be calculated. That's why we need nature spat algorithms. What these algorithms will do, initially they will have random weights of the low resolution images, okay, low precision images, in your words. And then these algorithms iteratively move in the search space. They will check with the fitness function and they eventually come up with a better weight. Initially you have random weights, but with the help of these algorithms, GWO or PGA, whatsoever algorithm you will take, you will have, after running these algorithms for few iterations, you will definitely have better weights as you are having initially. I hope I'm able to give the answer.
Dear participants, if you have any query regarding to today's session, kindly unmute yourself and ask the question to sir.
Hello.
Hello, Haji.
Good evening, sir.
Good evening.
Sir, I am Pinkal Jain from Gyananga College of Technology, Jabalpur.
Haji.
Sir, I am having a query. Sir, is there any criteria to decide how many iterations are required to solve our problem?
See, if you observe, basically this is depends upon the dimension of the problem. Okay. If the dimension of the problem is more, then definitely you have to run your algorithm for more number of iterations, for more number of function evaluations. And if the dimension is less number of iterations, I can say 50, 100 is sufficient. But for expensive problem in terms of dimensionality, if the dimensions are 1000, 2000, then it is advised to run your algorithms for large number of iterations, like 1000 or 2000, like this. So a correct boundary is not determined, but it depends upon an experiment. These algorithms are not making much time. So you just run it and you find yourself what is the best number of iterations in which you're getting the better results. Although you can not rely on a single run, you have to make multiple runs and take the average of it. Means you have to rely on the mean of the different runs.
So, sir, suppose I am performing my operation in multiple iterations and taking the average of mean of that particular operations or that particular results. So, how I can validate my results are efficient or not?
See, you run your algorithm, I can say at least 50 times on a particular problem. And whatsoever the best solution you're finding in those 50 runs, you take the average. And then if you compare it on to with other algorithm, you do the same, like average of 50 runs. And then you compare those means. And with the help of means or standard deviation, also there are some tests called Wilcoxon rank sum test, or there are other tests also, sign rank test. With those statistical tests, we'll try to compare the performance of these algorithms. And then we compare which one is best and which one is not performing good. Okay. We always want less standard deviation. We also want statistically better results.
Okay. Thank you so much, sir. Thank you, sir.
Thank you.
Vijay sir, one more question we received in the chat box. I think the question is random weight. So could you explain what is the random weight so participant will be satisfying with your answer?
See, random weight, I will explain with my slide, is that it is related to facial image super resolution. Like in this in this particular facial image super resolution method, we have mapping of low resolution images and HR high resolution images. These pairs of images we have available in our training set. Okay. Now I have an input phase which is low resolution. I want to generate this phase with the help of this training phases, this random training phases. Okay, random LR training phases. So I will use this equation in which I will try to minimize this input image with the help of this vector. So the weights are going to play the major role. Means I want to find the weights that will make this subtraction is 0. If this subtraction is 0, it means I'm able to generate an image identical to this input image. So my weights are the best weights I have got. The values of the weights is not known to me. So what I will do, I will randomly, just like in nature SPAD algorithms, we initialize solution randomly. But we know random solutions, we find one of them best. So we move it iteratively. Iteratively, they become better. And iteratively, we will find the best solution that will come up with the identical low resolution image. So those corresponding weights will multiply to the high resolution images and we get the resultant HR phase. Okay. I am also giving this link for better understanding. You can read this paper, Greyhound optimization algorithm for facial image super resolution, published in Springer. So you will have, this is a very interesting problem of face super resolution and you can have a better understanding.
Okay, sir, we got the reply from the question asked by the one of the participant. So, dear participant, if you have any query related to today's session, kindly raise your hand, then we will try to give the best answer for you. Okay, sir, I think there is no more queries. So thank you so much, sir. On a behalf of entire Atal team, as well as the from the Gyan Ganga College of Technology, I am very much thankful to you, sir, for delivering a very wonderful technical session, including the FSR, face, image, super resolution, and the real-time use of FSR, sir. You very nicely explain with the phototropic growth algorithm PGA equation explanation. Generally, the most of the participants are very difficult to understand how to collaborate the equations and how we will formulate the equations to generating the very good result. And the factor calculation also you very nicely explain in the very easiest way, and the step how